Hello guys. So today I'm gonna be solving some problems from chapter 6, which are trusses, and we're gonna start with the method of the joints. I selected this problem as the first one that I will solve today for you. It says, this steel truss bridge is in the Gallatin National Forest south of Bozeman, Montana. Suppose that one of the tandem trusses supporting the bridge is loaded as shown. This is the bridge, and this is one of the sides, which are the trusses. Determine the axial force in members AB, BC, BD, and BE. First of all, we don't have to solve all the members. In a real life situation, of course, you need to do everything, but this is an academic problem, so the only thing that we are asked to calculate is this member AB, this member BC, BD, and BE. How are we going to do that? Well, depends of what approach we want to take. What I want to do, because this is the objective of this video lecture or video problem, is use the method of the joints to solve that problem. First thing first, we have to check the supports that we have here, and this is, let's say that this is a pin and this is a roller, or vice versa. In reality, one of them should be a pin or a roller. In this case, they don't tell you which one it is, but I really don't care which one is the pin and which one is the roller because there is no horizontal force. So basically, what we will have as reactions is a reaction here at A, AY, and a reaction here at H, HY. Remember when we had a discussion about the method of the joints, that we said that we have to analyze each one of the joints like particle equilibrium, because this is exactly what we are doing. We're doing particle equilibrium around the joints. And one of the rules for doing particle equilibrium in 2D is that the maximum number of unknowns that you can have is 2, because the maximum number of equation of equilibrium that you have is 2 also, summation of forces in X and summation of forces in Y. So we have to look for joints with 2 unknowns to see if we can start without calculating reactions. And if you start checking, I have 1, 2, 3 unknowns, 1, 2, 3, there's not any. There's a couple of joints that I could start working, but I don't want to go there still, because anyway I'm going to have to calculate the reactions in order to do the rest of the problem. So let's start by doing reactions, and by doing reactions I'm going to do summation of moments at A, so I can calculate HY, summation of moments, or I can do summation of moments at H equals 0 to calculate A directly if I want to, and let's say this is the positive direction. So if that is what is happening, then I'm going to have 10 times 17 positive plus 20, plus 10 again, times 34, plus 10 again, times 51, minus AY times 68 equals 0. And with that, we can say that AY is equal to 15 kip. If I wanted to calculate HY, which is not the case here, I can do summation of forces in Y equals 0, and then I have that AY minus 10 minus 10 minus 10 plus HY equals 0. AY, I know it, and that will give me HY equal 15 kip. So we calculated the reactions, and we already wasted time by doing that. Because if you think, instead of start working, you will realize that this structure is geometric completely. And when I say geometric, you have the symmetric regarding the geometry. all the distances are the same spacing. If you draw a line here, it's exactly the same both sides. Everything is symmetric, geometric wise, and at the same time everything is symmetric load wise. So if you have, let's say, I don't know, let's say that you have a beam supported just here and here, and you have a weight at the center of 50. If this is exactly the center, well, this is going to take 25 and this is going to take 25, right? That's normal, that's logic. But in this case, because this is symmetric also, I can say that each one of them is going to take half of the vertical load. And the total load is 30, because it's 10 plus 10 plus 10. If I divide that by 2, that means that that's going to be 15, and that's going to be AY, and that's going to be HY. You see, this versus that. But of course, for doing that, you have to think and you have to be familiar with this type of situations. That's it. Now, you couldn't do that if you have a horizontal force, because if you have a horizontal force, then the symmetry, and means the symmetry, the body is not going to be symmetric load-wise. But if everything is symmetric, then you can do that. Okay, once you have that, we're going to start working at any joint that you want to. Let's start with the joint A here, at any joint that you want to know. The only joint that you can start is this, because now I know AY, and I have two unknowns here. I don't need this one, I only need this one, but I have two unknowns. So I'm going to start with that joint. I'm going to start with the joint A, and the joint A is this one here. Then you put the joint, and you put every single load or bar that is acting in that joint. This is the bar AC, or the member AC. This is the member AB here, and this is the reaction AY that I just calculated, which is 15. I know it's 15 keep, but I'm not going to keep repeating keep, so you know it's keep. And this angle here, I'm going to say is alpha, which is this one here, which by the way is the same one here. How do you know it's the same? Because it's symmetric, once again. So alpha, if you want to calculate alpha is going to be the inverse tangent of this distance divided by this distance, and this distance is 8 divided by 17, and alpha is going to be equal to 25.20 degrees. So now I have alpha. Now we can work and do the equation of equilibrium. My equation of equilibriums are summation of forces in X and summation of forces in Y. If I start by doing summation of forces in X, I'm going to have two unknowns. If I start by doing summation of forces in Y, the only unknown that I'm going to have is the vertical component of AB. So I'm going to do summation of forces in Y equals 0. And if I do that, then I have that AB, the vertical component of this, let me use the green color for that. The vertical the components of AB should be these two, right? So the vertical component of AB, which is this one here, is going to be AB sine alpha plus 15 is 0. And when you solve these for AB, AB is going to be negative 35.23 kip. Remember, that negative sign, what indicates is that the direction that I assumed here, it was wrong. And the correct direction for AB is the opposite of what I assumed initially. What I recommend you to do is that immediately, if you get that value there negative, immediately change the direction in your drawing over there. And at the same time, put a reminder for you here, which the correct value for AB, which is going to be like that, 35.23, the value for AB, the correct value for AB is going to be 35.23 kips. And also put the characteristics of that force, if it's tension or compression. And as we discussed before, when you have the tension entering or the force entering into the joint, that indicates that the bar is going to be subject to compression. So put a big C here and frame that. And you know when you do your summary table that that member is at compression. And then you don't mess up when you go to the next step. From here, I don't have to do summation of forces in x equals 0 for calculating AC, because for this particular problem, I don't need it for anything. So I'm not going to even calculate that. And then I'm going to go to the joint C. And my joint C has one force here called BC, which is this one. I have this other force, external force applied of 10 kip here. And I have this unknown and this unknown here. This is AC and this is CE. Oh, but wait a second. I have three unknowns. And I say that in a particle equilibrium, the only thing that we can have is two unknowns because we have two equations. So that means that this AC, even though I'm not asked for it, I have to calculate it in this step to put it here. No, I don't have to. Why is that? Because if you look this closely, my two equations of equilibrium are summation of forces in X and summation of forces in Y. The one that I have to calculate is BC. That's the one I'm asked to calculate. So if I do summation of forces in Y equals 0, directly these two forces are parallel and they go in the X direction. Parallel, no, I mean collinear, and they go in the same direction over there. So if I do summation of forces in Y equals 0, directly I can get that BC is equal to 10 kip, even though I had three unknowns. And that's my second of the values that I have to calculate. Is going in this direction. And because it's going in this direction, this is the force BC, remember, and it's leaving the joint, that means that that force is in tension. Now we have two of them done. AB done, BC done. Now we have to go to BD and BE. Okay, let's study that. For BE and for BD and BE. So if I'm gonna go for BD and BE, let's say that I go to the joint B. Well, if I go to the joint B, how many unknowns do I have? These I know, and I have two unknowns. Yes, I can go to the joint B and calculate that. Go to the joint B. I have my joint B here. This is AB. And this is the critical part of these type of problems. You have to come back to the original calculation for AB and look the direction that that force is going to. You see, I assumed that it was leaving the joint, but there's actually in compression entering in the joint. That means that if in that joint, at that point, was entering in the joint, here, and this element is going to also be entering in the joint. Because this bar is connected. This is like if it was here, you see? This is like this, and this is the bar. This is this bar here. So if this is the bar, and here is entering in the joint, there is going to be also entering in the joint, just for equilibrium. Now I have that direction correct. The other issue here could be BC, and BC, it was leaving the joint here. So BC here is going to be also leaving the joint, and that value I calculated as 10. This value for AB I calculated before, and it was 35.23. Also, I know this angle here because I did it before also. That angle is alpha, and I had the value for alpha. Now I go to my unknowns, and my unknowns are BD and BE. BD and BE. Well, I'm gonna say, I'm not even gonna think about it, because this is the first problem that I'm doing, and I'm assuming that don't have very much practice doing this. So this angle also is alpha because it's the same angle here, and this force is called BE, and this force is called BD. So if I do here, once again, summation of forces in X equals 0, I'm going to have two unknowns going in the X direction. Because if I do summation of forces in Y equals 0, the only unknown is going to be the Y component of BE. And that's what I'm going to do. So I'm gonna do summation of forces in Y equals 0. And if you do summation of forces in Y equals 0, then you have this component, which is 35.23 sine of the angle, because remember, it's going to be this component, sine of alpha. And then I have the vertical component of BE, which is this side, and it's going to be BE sine of alpha also, but negative because it's pointing downwards. BE sine of alpha equals 0, and then I can calculate BE. Or I missed something. Yes, you see, and that can happen to you also, because this here and this here are BE minus this other force, which is here, 10 minus 10 equals 0. And when you solve this equation, then you get that BE is equal to 11.74 kip. That's the value for BE. 11.74 kip. That's BE. That value for BE, if you look, this is here, this is the joint B, this is BE, and it's leaving the joint. If it's leaving the joint, I know this is going to be in tension. So we have BE. And now we look for BD, which is the last one. For BD, which is this one, I do summation of forces in X equals 0. And when we do summation of forces in X equals 0, we have AB. Now, this is the component that I'm looking for. So it's cosine, AB cosine alpha. This is the component that I'm looking for, BE cosine alpha also, pointing to the right, positive, plus BD equals 0. BE, I know, AB, I know, and alpha is also known. Alpha, it was 25.20 degrees, we calculated before. So you put the alpha, the AB, and the BE here and solve for BD. When you solve for BD, you're going to get that BD is negative 42.5 kip. Negative means that if this is my joint B and BD originally was here, now BD is going to go opposite to whatever I had. Meaning BD is going to be acting here. It's going to be 42.5 kip. That's BD. And because it's entering into the joint, that force is going to be in compression. Let me copy here compression, because if I put C, somebody might think that I'm analyzing the joint C. By the way, if you look at this before, you could have realized that this direction has to go to the left immediately, because it doesn't matter, as you can see, because when you solve it, the negative sign is going to tell you that what you did was in the opposite direction, because it has to go in the opposite direction because you mess it up with the sign here. But if you look at this and do a little bit of analysis, just a mental analysis before start working, then you will see that the horizontal component of AB go to the right, the horizontal component of BE go to the right, and the only thing that can possibly oppose to that is the force BD. So that force BD should be pointing to the left immediately, and you don't have to change the sign after that. But anyway, it doesn't matter because it's just a change of sign. Now at the end, remember, you build like a summary table, and in that summary table you're gonna put how many forces I have, 4 forces, then I need 5 spaces here, 5 spaces, and I'm gonna have 1 for the member, 1 for the value, 1 for the tension compression. So it's gonna be member, value, tension or compression, and I'm gonna add this for the units. So the members are AB, BC, BD, and BE. Those are the members that we are asked to, and we start looking for them. I have BD here. BD is 42.5. Keep, and that's 42.5 keep are in compression because it's entering in the joint. All the units are keep in this case. Now the next one that we have is BE, and BE was 11.74 keep, and it was also in tension. Why tension? Because it was leaving the joint. And the other one was BC, which was 10, and it was leaving the joint. That means tension. And the other one was, the first one that we calculated was 35.23 entering into the joint, which is compression. So 35.23 entering in the joint means compression. And that will be the first example for the method of the joints. Thank you for watching, and I will be recording more examples for you guys. Have a good day.